After takeoff and landing performance, let's take a look at climb performance. Most of the factors that affect takeoff performance affect climb performance as well. Let's discuss some of the important climb speeds first. Vx, best angle of climb speed. This is used to gain most altitude in a given amount of distance, basically gaining the maximum altitude with the least amount of distance. This airspeed is the lowest of all the climb speeds and requires a high pitch attitude, usually limiting the forward visibility. Use this airspeed to clear obstacles when they are closer to the runway on departure. After that, we have the Vy, which is the best rate of climb speed. As the name suggests, Vy gives you the best rate of climb, meaning giving the maximum altitude gain in the least amount of time. Vy is usually used for normal takeoffs. Then comes the cruise climb speed. Cruise climb speed is generally the highest of all the climb speeds. The rate of climb is the lowest. In addition to better engine cooling and improved forward visibility, faster climb speed provides you a better cross-country performance, better cross-country speed, cutting down the total time en route. How does it improve engine cooling? Because cruise climb speed requires a lower pitch attitude than the remaining climb speeds. This lower altitude gets more air flowing through the engine, hence increasing the engine cooling. If you remember from our discussion of aerodynamics, an airplane must have an excess thrust and not lift to have a sustained climb. Also, the performance of propeller-driven airplanes decreases with altitude as they lose the power and the thrust with increasing altitude. This causes a change in climb speeds as well. Take a look at this picture of how the climb speeds change with altitude, and let's keep this picture here for a while. If you look at it, when the airplane reaches an altitude where it can no longer climb further, it has reached the absolute ceiling. This altitude is called the absolute ceiling for the airplane. Remember, this ceiling is expressed in terms of density altitude. So keep this in mind that on a particular day when the density altitude is higher than the true altitude, you would have reached your absolute ceiling at an indicated altitude which is lower than the numbers you see on the POS. Another very important altitude while we are discussing, and it is present in this chart as well, is the service ceiling. This refers to the altitude where a single engine airplane is able to maintain a maximum climb of only 100 feet per minute. That is when you pitch for Vy. When you pitch for Vy and are only able to maintain maximum climb rate of 100 feet per minute, you have reached your service ceiling. This altitude is more commonly used than the absolute ceiling because it represents the airplane's practical ceiling. You would find that in most POHs written in the general section. These are the things that we covered when we were talking about climb performance. Now obviously it is time for examples. So let's get Pilot Chintan Patel back. And I'm back. Let's see the climb performance charts of different general aviation airplanes. Usually for single engine general aviation airplanes, there are two common charts available in most of the POH. That is maximum rate of climb charts and time, fuel and distance to climb charts. So let's take a look at them. Maximum rate of climb charts. Again, this is for Cessna 172 at 2,550 pounds. Conditions: flaps up, full throttle. In this particular table, you see the left column to be of pressure altitude in feet, and then you see the top row, pressure altitude, climb speed, rate of climb in feet per minute for different temperatures, -20, 0, 20 and 40 degrees. If you have temperatures in between, you already know how to interpolate, so you have to find out those values by interpolating. How to use this chart is pretty simple. Most of the figures are straightforward. For example, let's say you were climbing from sea level at 0 degrees. The maximum rate of climb that can be achieved with flaps up, full throttle at Vy is 785 feet. That's pretty much it. That's all the information that you can get from here. It is the maximum rate of climb that you can maintain at a particular altitude at a particular temperature. Then you have a note that mixture leaned above 3000 feet pressure altitude for maximum RPM. That's it. That's pretty much the maximum rate of climb table. The next table is time, fuel and distance to climb at 2550 pounds again. Conditions: flaps up, full throttle, standard temperature. The left column is talking about pressure altitude in feet from sea level all the way up to 12,000, and the top row says pressure altitude, temperature, climb speed in knots, indicated airspeed, rate of climb feet per minute, and from sea level time, fuel and distance to climb. This is very important. From sea level note is what is usually overlooked in the beginning part of our training. So let's take a simple example. Let's say I want to climb from sea level to an altitude of 2000 feet. My time for that particular climb would be 3 minutes. My fuel used in gallons would be 0.8, and my distance that is required for the climb is 4 nautical miles. That's it. But let's say I'm at an airport that is at 2000 feet and I want to climb to an altitude of 8000 feet for my cruising. What do I need to do now? You need to calculate the fuel required or time, fuel and distance required to climb from sea level to 2000 and from sea level to 8000, and then subtract those values. So in our case, for 2000 it is 3.8 and 4. For 8000 it is 14, 3 and 19 nautical miles. So for the climb from the airport at 2000 to an altitude of 8000, my time would be 14 minus 3, 11 minutes. Fuel required would be 3 minus 0.8, 2.2 gallons. Distance I need is 19 minus 4, that is 15 nautical miles. This is my time, fuel and distance required to climb from 2000 to 8000. That is how you use the chart. Then you have notes underneath talking about add 1.4 gallons of fuel for engine start, taxi and takeoff allowance. This needs to be added to the gallons used so that you have an idea of how much fuel is it gonna take from the moment you start the engine to all the way reaching your cruising altitude. 1.4 gallons are a considerate amount for start, taxi and run up and takeoff. Then mixture leaned above 3000 feet pressure altitude for maximum RPM. Increase time, fuel and distance by 10% for each 10 degrees above standard. Distances shown are based on 0 winds. Alright, one important thing here I would like to mention is that the third note that talks about increasing time, fuel and distance by 10% for each 10 degrees above standard, I like to take the temperature of the airport that I'm going from or the airport I'm departing from. Let's say I'm departing from an airport at around sea level. The standard temperature at sea level should be 15 degrees Celsius. But on a particular day, it is hot summer afternoon where it is 25 degrees Celsius. So right now the temperature is 10 degrees above standard. This 10 degrees above standard needs an increase in the time, fuel and distance by 10%. It makes sense for me to use the temperature of the airport I'm departing because while performing the airplane is around that area, is starting from the airport, so the performance should be calculated based on the temperatures of that airport. Now this is for a single engine general aviation airplane. You might have a multi-engine airplane in which you are doing your training. In that case, the multi-engine airplane also has single engine, inoperative, rate of climb, etc. Some additional charts in addition to these two what we have already discussed. Now I covered them all in the module for transitioning to a multi-engine airplane, so I'm not gonna repeat it over here. And if you are interested, make sure you look into that particular module as well.